This is the second part of section 6.3. We're going to continue to talk about volumes for solids of revolution. And instead of the disk method, we're now going to talk about something called the washer method. This is going to allow us to find the volume of solids when the original region, the R, does not sit right on the axis of revolution. Take a look at this as an example. The region that we started with was the region between y equals 2x and y equals x squared. So it was this region right here. It was then revolved around the y-axis, creating this shape here. Notice that you've got the straight lines here in the middle. So you've got this solid surface going around, but it's hollow in the middle. Right? It's like that shape with that cone cut out of it, if you will. So our goal then is going to be to find the volume of that hollow shape. The way we're going to do it, just like before, is to imagine taking a little representative rectangle right in here and rotating just that one rectangle around the axis. What ends up getting created is not just a disk, but a disk with that hole in the middle, right there. And that's what we're calling a washer. So we create this washer shape, the solid disk on the outside and then the hole in the middle. The way that we're going to go about finding our volume is essentially by finding the volume of the whole thing as if it were solid and then subtracting out the piece that's the hole in the middle. So what I'll end up with here is actually two radiuses. The large radius is going to go all the way out to the far edge, and then the small radius that goes out to the edge of the hole. And we'll end up taking essentially two disk methods and subtracting them. We'll take the volume of the solid or the outer disk and subtract the volume of the hole, the inner disk. Fortunately, we already know how to do the disk method, so this isn't going to be too bad. If I call capital R the larger radius to the outside edge, the volume of that would be pi times capital R squared h. And then if I call little r the radius to the inside, the hole, the volume of that would be pi times little r squared h. And so that's just going to be how I'll find the volume of my washer as I go around. And then, of course, we'll add them up, or in other words, integrate over our entire shape. Let's try this example. We're going to go back to this, and we're going to actually work out the volume using this washer method. So I'm going to draw a little bit better graph here of my picture. We've got y equals x squared and y equals 2x. And I'm going to number here. So let's see, y equals x squared, just a parabola. Like so. And then y equals 2x will be a line with slope 2. See, it would go through 1, 2, and 2, 4. Going to be the intersection point, actually. And so the shape that I'm rotating is this little slice in here. All right. We are rotating around the y-axis, so we're going around this way. And that means that I need to use horizontal rectangles. Again, they always have to be perpendicular to the axis of rotation. So I'm going to say my large radius goes from the axis of rotation all the way out to the outer edge. There's my capital R. And then to create the whole, I'll go from that axis of rotation just to the inner edge. The H, same for both, is just a little piece of the y-axis, so we'll call that delta y. Now, because we are using delta y and horizontal rectangles, that means that I have to have functions of y. In other words, I have to solve these equations for x. So instead of y equals x squared, I'm going to think of this as x equals the square root of y. Again, going with the positive square root because I'm in the first quadrant where all the x's are positive. And instead of y equals 2x, we'll go with x equals y over 2. All right, so thickness h, that's the delta y. Capital R goes to the parabola. The x value is square root y. And little r goes to the line. X is y over 2. We go with our washer method. I'm going to put the equation up here. Volume of the washer. Oh, and I probably should have said something back here. I'm sorry. Go back one page for me, if you would, please. Just to make the arithmetic or the integral a little bit easier, usually we actually factor out the pi. Call this r squared minus little r squared, and then also factor out the h. I know I put one in the front and one in the back. That's because the h is usually the delta x or the delta y. It becomes the differential, so it just kind of makes sense to write it that way. So this is the equation that I will be using for the volume of the washer in the factored form. So again, pi, capital R squared minus little r squared times h. So for this particular situation, the volume of one washer would be pi times capital R is square root y. We square that. Minus little r is y over 2. Square that. Times h, which is our delta y. To get the volume of the entire solid then, we want to integrate this, and like I've often done, we'll pull the pi out of the integral. Let's see. Square root of y squared is just y. I can write that as y squared over 4. And the delta y becomes a dy. Y is my variable of integration, so I need y values for the limits. We start down here at y equals 0. And this intersection point really is 2, 4. I drew it that way, but you can see it, right? 2 squared is 4, and 2 times 2 is 4. Or, of course, you could have also graphed on a calculator or something like that. But that upper limit really is 4. All right. I just went ahead and ran this one on the calculator. Maybe we'll do one or two by hand, but we'll use our calculator to make things a little quicker here. The integral did come out to a nice fraction. It was 8/3. So I'm going to write my final answer as 8 pi over 3, or 8/3 pi. Either way would be fine. All right, we're going to stick with this same picture for the next several examples, and we're going to rotate it around different axes. So, before I do that, just a quick summary page. I've actually got this one all filled out because it's so similar to the last one. You also have this in your filled out notes section of your course pack. But notice what we've got here is if we've got our vertical rectangles, so we're looking at functions of x, then the volume of our washer would be the large radius f of x squared minus the small radius g of x squared times pi times dx. integrate to get the volume. And if we've got horizontal rectangles, so our functions are functions of y, we have pi times large radius is g of y squared minus small radius f of y squared, and again integrating to get the volume. So I won't spend extra time on that. It's just a small step from our disk method. And again, that's also filled out for you in your filled out notes. All right, so let's go on to the example that we were working on. Same thing here. We still have the y equals x squared and the y equal 2x. But this time I'm going to revolve around a different line. Instead of rotating around the y-axis, I want to rotate around the vertical line, x equals 2. Let's see how that works. I'm going to start by just sort of quickly drawing my shape again. The parabola. And then the line. All right, this time our axis that we're rotating around is the vertical line x equals 2, which happens to go right through this intersection point. So let me draw that in as our axis of rotation. And when I go to draw my representative rectangles, once again, I always want to draw perpendicular to the axis of rotation. So these are going to be horizontal again. And I always want to draw my rectangles so they end on that axis of rotation. So this time, from the axis of rotation to the furthest part of our region would go to the line. There's the capital R. And to create the whole, I would go from the axis of rotation to the closer curve. There's my little r. The heights for both of these, again, little piece in the y direction, so delta y. So let's make our list. H is delta y. For capital R, since I'm not on the y-axis this time, I have to use right minus left. The right side of this would be at x equal 2, minus the left side, and since we're going horizontal, I do need my alternative forms here, x equals y over 2, and x equals the square root of y again. So let's see, in this case we would have 2 is the right, the left is the line. So that would be y over 2. Same thing for little r, right minus left. The right is at x equal 2, and the left is on the parabola, which is the square root of y. So the volume of the washer, pi times capital R squared minus little r squared times h. It's going to be pi times capital R, 2 minus y over 2, square that, minus little r, 2 minus the square root of y, square that, all times h, which is our delta y. All right, let's set this one up as our integral then. To get the volume of the whole thing, we'll integrate. I'm going to pull the pi out. And If I was really going to iterate this by hand, I would have to square both of those out. It's kind of a pain, so in this case, I'm going to be really glad that I can use the calculator. I'm not going to bother squaring them out. I'll just type them into the calculator just like this. And once again, the variable of integration is y, so I want to use y values for my limits. So y starts at 0, and the top y value would be 4. Again, I did run this through my calculator, and I got 64/15ths. So I could write my final answer as 64 pi over 15. All right. Apologize, I'm probably going to make you sick of this shape, but we're going to stick with it for another problem or two. In the next problem, we once again have our same region bounded by y equals x squared and y equals 2x. But this time, we're going to revolve the region around the x-axis. So, take a moment, draw your graph again. And this time our axis of rotation is the x-axis. All right, so we go with our usual idea. The representative rectangle needs to be perpendicular to the axis of rotation. So if I go from the x-axis to the further graph, capital R is going to go all the way up to the line. And then small r is going to go from the axis to the closer graph, the parabola. There's little r. In both cases, the base of the rectangle, or the height of the disk, is going to be a little piece of the x-axis, so we'll go with delta x. So, h is delta x. Capital R is the line. And by the way, notice with vertical rectangles, we do want y values. So we're going to go with y equals 2x. We don't have to resolve. Just 2x and it ends on 0, so I don't have to subtract anything. Technically, it's 2x minus 0, but when we're on the axis, I don't usually bother writing the subtraction. Little r is on the parabola, so that would be x squared. And the volume of my washer is going to be pi times 2x all squared minus x squared squared times, delta x. All right, so there's my setup. To get the volume of the entire solid of revolution, I'm going to integrate, and that would actually be 4x squared minus x to the 4th dx. And when I did that, I got 64 pi over 15. You know what, you guys? I am so sorry. Making these videos and juggling papers, sometimes I look at the wrong thing. That is correct, by the way. That is the right answer. The previous one, I think I skipped a line because I had pre-written out my calculator values for you, so we'll go back to that for just a second. But there we go. My apologies on this one. I looked at the wrong thing when I was looking at my pre-done calculator work. This one where we were rotating around x equals 2, that actually came out to pi times 8/3. Or 8 pi over 3. Sorry about that. All right, we're going to use this graph one more time. And this time, we are going to rotate the region around the line y equals -3. So I know you're sick of drawing this, or I probably should have drawn it for you. There's our very familiar shape. And this time my axis of rotation is y equals -3. All right, so when I go to draw my representative rectangles, I always have to start at the axis of rotation. And for capital R, I'm going to go all the way to the further graph, which would be the line. So my capital R is all of this. Small r goes from the axis of rotation to the closer graph, so that would be in here. And h, for both of these, a little piece in the x direction, so h is delta x. So capital R. This time, since I don't stop at the x-axis but go all the way down to here, I'm going to think top minus bottom. And the top of this rectangle is on the line y equals 2x, minus the bottom, which is at y equals -3. So 2x plus 3 is capital R. Lowercase r, again, top minus bottom. The top is the parabola, so x squared. The bottom is again at the y equals -3 line, so x squared plus 3 is r. And the volume of my washer is going to look like pi times. Capital R would be 2x plus 3, square that, minus little r, x squared plus 3, square that, times delta x. To find the volume of the entire solid, then we'll integrate. And let's see, we'll pull the pi out. My integrand is, if I was going to do this by hand, I'd actually have to square these out, but again, I'm just going to use the calculator for speed here. This is a dx integral. So in my picture back here, the x's would go from 0, and the x values stop right here at 2. When I did this one on the calculator, I ended up with 184 over 15. And then, of course, I end up multiplying it by pi. So 184 pi over 15. All right, we're finally done with that shape, but I just wanted you to see some of the different variations when we change the axis of rotation. We'll do a last few examples now with some different shapes. In example 4, we want to look at the area that's captured between the graph of this upside down parabola and the line y equal 3. And we'd like to generate a volume by rotating around the line y equal 1. Right? This one, it probably would be helpful to have a calculator or computer graph for. It's probably a little easier for you to see it if I do it on Desmos, but again, you can do this on your calculator as well. So our parabola y equals minus x squared plus 6x plus 3. Our line y equals 3. Oh, it's even bigger than that. Look at that. Oh, I'm sorry, I changed the wrong number. No wonder that didn't work. It's the y value that I got to change. There we go. Oh, I changed the x value as well. Goodness, my Windows skills are not good. There we go, finally. All right, so here is our picture. I got an intersection point here at 0, 3, and another one there at 6, 3. So let me see if I can just move this window over a little bit, and we will sketch that. I'm not going to try and be super accurate here. I'm just going to kind of sketch the general idea. So this is the parabola. This was the line y equals 3. And we've got 0, 3 is this intersection point, and 6, 3 is this one. And I actually didn't even try to make it so that it looked right on this axis. I just labeling it and calling it good. So we can now see our region. We want to rotate this around the line y equal 1. Clearly, the region does not sit right on the axis of rotation. Therefore, it will create a hole when I rotate, and I need a washer method. So, to get my capital R, I draw my representative rectangle from the axis of rotation to the graph that's further away, which in this case is the parabola. And a little r from the axis of rotation to the closer graph, which is the horizontal line. The heights or thicknesses of my disk will be little pieces in the x direction, so delta x. And let's see, capital R, we are looking at y equals here, so thank goodness I don't have to try to solve that for x. That wouldn't be fun, right? Capital R would be top minus bottom. Top is the parabola, minus the bottom, which is just the line y equal 1. So I'd actually have minus x squared plus 6x plus 2. Little r, top is just y equals 3, minus the bottom, which is y equals 1. So little r is just constant, it's 2. And notice that's true. The radius of the hole that I'm creating is just this constant value of 2 all the way through. All right, so the volume of my washer is going to be capital R squared subtract little r squared times the h, and to get the volume of the whole solid, we'll integrate. And I could, but definitely don't want to have to multiply that out, which is what I'd have to do by hand. Instead, we'll use our calculator's handy little feature here. 2 squared, I'll just make that a 4. And for my limits of integration, these are x values. So the x values would run from 0 at this intersection point to 6 at that intersection point. All right, let's see. I did do this one. I got 2016 over 5 from the integral, and then of course times that pi. All right, let's take a look at example 5. This time I want the volume of the solid generated by revolving the region bounded by the graphs of y equals ln x, y equals 0, x equals 1, and x equals 3 about the y-axis. This one I can probably graph by hand. Y equals ln x, know what that one looks like, right? It's just got a vertical asymptote going down the negative y-axis. The x-intercept is here at 1, and then it just sort of goes up slowly from there. Something like that. All right. Y equals 0, so the x-axis is also a boundary. And then x equals 1 and x equals 3. X equals 1 is actually the intersection point right here. And then x equals 3 over here. And that defines my region. All right, we're rotating around the y-axis. And that intersection point was definitely 1, 0. This one, since I didn't graph on a calculator or Desmos, I'm just going to do it by hand. Since x is 3, y would be the natural log of 3. So this point is actually 3 comma ln 3. All right. Large radius. First of all, we're rotating around the y-axis, so perpendicular to the y-axis, we're going to go with horizontal rectangles. And our large radius then goes from that axis to the further graph, which is the vertical line. small radius from that y-axis over here to the closer graph, the log graph. And the h's are little pieces of the y-axis, so delta y. Okay, since we're horizontal, I do need this to be an x equals. So if I solve my equation here for x, I'd have x equals e to the y. So my large radius would be e to the y, technically minus 0, or just e to the y. I'm sorry, let's try that again. That's the small radius. The large radius goes all the way to the vertical line. The large radius is 3. The small radius goes to the curve, so that's the one that's e to the y. And then I'm ready to set up the volume of my washer. All right. So I would have r squared, or 3 squared for the capital R, minus little r is e to the y, square that, times delta y. And then when I integrate to get the volume of the entire solid of revolution, I'm integrating 9 minus e to the 2y dy. And these are y integrals, so I need y values for my limits. The y value here would be 0, and the y value up here at the intersection point is ln 3. This one, I just want to show you this on the calculator because this happens sometimes, but we haven't talked about it a ton. If I type this integral just that way into my calculator, I get something that if I try to change it to a fraction, it doesn't work. This is just a decimal. It's not surprising with the log in here, right? This is just a decimal that goes on forever with no particular pattern. And therefore, what I'm going to end up doing for my final answer is just saying, let's do a decimal approximation. I'm going to multiply it out by pi, and it's about 18.496. So if you don't get a nice fraction times pi, just feel free to use the decimal in your final answer. All right, we've got one more example. In this last one, we're looking for the volume of the solid generated when we revolve the region bounded by the graphs of xy equals 5, y equals 2, y equals 5, and x equals 5. A lot of boundaries about the line x equals 6. Let's go ahead and graph this one, and I'm going to use Desmos just to make it big enough for you to see, although, again, if you solved this for y, which isn't hard, right, you could do it on your calculator. So let's see, my first equation is xy equals 5, and then we have y equals 2, y equals 5, and x equals 5. And let's see here. I'm going to go negative 10 to 10. And that's probably a little bigger than we need on the y. Let's just do 10 there as well. Okay, there we go. Right in here, this little piece is bounded by all 4 of my graphs. It's bounded by the green curve, which is the xy equals 5. It's bounded by the blue one, y equal 2. The black one, y equal 5, and the red one, x equal 5. So it's this little region in here that I'm trying to rotate. Okay. I'm going to go ahead and see if I can sketch that for myself. Let's see here. We've got we've got y equal 2 and y equal 5. Let's start with those. 1, 2, 3, 4, 5, 2. We've got x equal 5 over here. And then the xy equals 5 kind of comes down and cuts through like this. Let me use a different color. Okay. The other piece of that curve is over here, but since it doesn't have anything to do with my region, I'm not going to bother drawing it. All right, let's get intersection points while we're here. That one's 1, 5. That one's obviously 5, 5. This one is clearly 2, 5. And then that one is 2.5, 2. Good heavens, I think I need to take a break. I am making mistakes all over the place. Sorry, this is 5, 2. And then this one is 2.5, 2. So we got a model to use as needed. All right, there's my region. We are rotating around the line x equals 6. So there's the axis of rotation. Okay, our representative rectangles have to be perpendicular to the axis of rotation. So in this case, that would be horizontal. And I'll draw capital R from the axis of rotation to the graph that's further away. And I'll draw little r from the axis of rotation to the closer graph, which is just this vertical line. The heights of the disks are little pieces in the y direction, so delta y. And my capital R, I'm going to have to go right minus left. And let's see, since we're going horizontal, I need the x equals form. So I'm going to go ahead and take this and solve it for x. X would be 5 divided by y. So, right minus left. For capital R, the right is over here at x equals 6. And the left is on the curve, which is x equals 5 over y. Little r, same idea, right minus left. Right is x equals 6 again. And left is on this vertical line x equals 5. So actually little r this time is just going to be 1. Volume of the washer. Let's see, capital R is 6 minus 5 over y. Square that. Little r is just 1. And h is delta y. So to get the volume of the entire solid, we will integrate. And again, I would have to multiply that out if I were doing it by hand, but since I'm not, I'll just type it into the calculator that way. This is a delta y, it's a dy integral, so I need y values for my limits of integration. The bottom of this is at y equal 2. The top is at y equal 5. And this one, when I plugged it into my calculator, it did not come out evenly to a nice fraction, so I just went ahead and multiplied the pi right into it. The integral came out to 57.523, etc., etc. So I just did the multiplication by pi for a final answer of about 180.712. So there's your disk method for finding volumes of solids of revolution. And that brings us to the end of 6.3.